Hello and welcome to my channel. In today's video, we are going to be solving this problem that has a uniform distributed load acting on this beam, and the beam has two supports, and these two supports are resisting the forces that are pointing downward. So the forces that are pointed downward here will be resisted by these two supports, right? So in order to solve problem like this, the very first thing you have to understand is to figure out the type of support and the directions of the forces. So in our case here, we have a roller support. For a roller support, you will always have a vertical force. You are not going to have a horizontal force, because as you can see here, this is a ruler, and as you try to push this beam on the right or on the left, it is not going to resist that. It is going to go in the directions of the applied action, right? So let's say, for instance, if you apply a force on this beam here, try to push this on the left, as a result, this ruler is going to slide going on the left, right? So because of this, we don't have any force in this horizontal direction. But as you try to push down on this beam from the top down, it's going to resist that. So because of that, we're going to have a vertical force here. So this pin support, we get a vertical force. This vertical force is going upward. We call this FB, right? And I'm sorry, this is not a pin support, it is a roller support. For this one, it is also a pin support. So if you have a pin support, you will always have two forces acting on the beam, right? So for this pin support, as you try to push down on this beam from the top, there will be a force that will be resisting your action too as well. And as you try to push on the left or on the right, it is not going to allow you to push through it, because it will be resisting that. It is not on a roller here. So because of that, there will be a force going in the direction opposite to your action. So let's say, for instance, if you are pushing this beam on the right, there will be a force going on the left, right? And if you are also pushing this beam on the left, there will also be a force that will be resisting your action, which will be going on the right. So in this case, as you can see, this beam, we have a horizontal force that is going on the right here, that horizontal force, and that horizontal force is 6 kilonewton. And we also have another horizontal force that is going on the left, that which is 2 kilonewton. So in this case, we try to understand something here. We have 2 kilonewton here. We also have 6 kilonewton here, right? In order for this beam to be balanced, we should have a force that is going to add up to this one to equal this value. Since we have 6 kilonewton force that is going on the right, that means we should also have 6 kilonewton force that is going on the left, right? In order to balance the force. So in order for your calculations to always be right, you must make sure that your forces are balanced. So in this case, you have 6 kilonewton force that is going on the right. Make sure that the forces that are going on the right, on the left, should also be 6 kilonewton. So by placing FAX, which is the horizontal force due to this pin support, on the right, it is going to make this problem wrong. Because as you can see, if you place the FAX on the right, that it is pointing on the right, it is going to be added to this value, making this value larger than the value that is going on the left. So it's going to be wrong. So in this case, we know that the value here is larger than the value here, right? So in this case, we are going to draw the arrow pointing in this direction. Pointing in this direction. So this is the horizontal force due to this pin support. And the pin support also, it has a vertical force too as well. So we have a vertical force here. We call this FA, right? Then we also call this FAX. So now we have 3 unknown forces, and these 3 unknown forces are what we are going to solve now by the help of the equilibrium equations. So we will basically have to sum all of these forces and set them equal to 0. So the sum of the horizontal forces must be equal to 0, and the sum of the vertical forces must also be equal to 0. After that, we are also going to solve for the moment in order to find these 2 unknown forces. So let's get started with the calculation. There are 3 equilibrium equations that we need to carry on our calculations. So the first one we need right now is the sum of the forces. The sum of all the forces in the x direction must be equal to 0. Right? So in this case, we have a force that is going on the right. It should be equal to the forces that are going on the left. So on the left here, we have we have 2 kilonewton plus FAX. Notice that it is going in the same direction. We said that equals to 6 kilonewton. Alright, so solving for FAX here, we're gonna have 6 kilonewton minus 2 kilonewton. So FAX is therefore 4 kilonewton. This 4 kilonewton force makes sense because we have 2 kilonewton force that is going on the left here, right? So therefore, we should also have 4 kilonewton force that should be going on the left in order to make this 6 kilonewton force. So that is going to balance our forces in the x direction. So in this case, the forces are balanced, right? So the next calculation we need to carry on is to perform the summations of the forces in the y direction. And in this case, we have 3 forces that are going up. We also have a force that is coming down. Notice that we have a uniform distributed load here. So we are going to convert this to single load, single pointed load, that which is going to be acting in the middle of this distributed load. If you look at this beam, we have a uniform distributed load here, right? And since this is a rectangular distributed load, we are going to multiply this height, which is considered to be 4 kilonewton per meter, by the base here. 4 times 5 is going to give us 20, right? So we have 20 kilonewton force here. It's going to be acting in the middle of this distributed load. Since this uniform distributed load is 5 meters long, the force acting on this uniform distributed load is going to be in the middle of this uniform distributed load. So in this case, it's going to be acting 2.5 meters away from the beginning, right? Because it is 5 meters. So let's try to sum the forces in the y direction. So the sum of the forces in the y direction in the y direction is we have FA, which is going up, FA, plus we have FB, which is also going up. Oh, FB. Then we also have 4 kilonewton force, which is also going up. Then we set that equals to the forces that are coming down. We have here 4 kilonewton force that is coming down. And we also have 20 kilonewton force that is coming down. And the distance, we're going to consider the distance here as 2.5 and here as 2.5 plus 20, right? So now performing this calculation, we will have F A plus FB, which is going to be 24, a 4 from this one. We have 24 here. So minus 4 here is going to just give us 20. So in this case, we get FA plus FB, which is going to give us 20 here. So the next thing we have to do is to calculate the unknown forces here. So now we have 2 unknown forces, which is FA and FB, right? So in order to calculate these 2 unknown forces, we will need the moment equation. So the moment equation is about A here. We set that equal to 0. But before we perform the moment calculation, let me try to remind you about some things that you need to know. So for moment is just the force down the distance, right? So let's say, for instance, if we are going to consider taking the moment about point A here, right? So the force here, which is this 4 kilonewton here, is going to be multiplied by the distance away from this point A. So that is going to be the moment. For instance, if you have a force like this pointing downward and you are taking a moment about A here, all right? And the distance is from this force to this A. You are just going to multiply this force by this distance D, right? So the force will be multiplied by this D. So in this case, you're going to have ND, which is just going to be equal to our moment, all right? So we're also going to be considering taking the moment in the anti-clockwise directions as positive. So taking the moment about point A here, we have the distance from 4 kilonewton force to this A, it is just 1, right? And this 4 kilonewton force is going in an anti-clockwise direction. So in this case, we have the moment about A is going to be 4, because it is positive. 4 multiplied by 1, right? Then the next force here, the next force is this one, which is FB. Notice that we're not going to consider this one because it is a force that we are considering taking our moment about. So this is what we're going to consider, right? And we have the next force, which is FB. The distance from A to FB is 1. We have 2, so it's going to be 3. Since it is going also in an anti-clockwise direction, we're going to consider as positive. So this is going to be plus 3FB. So now the next force is this 20 kilonewton force that is coming down. So this 20 kilonewton force is going in a clockwise directions, which is going to make it negative. So we have negative 20. Since we have 2.5 here as a distance from here to here, and we also have 1. So distance away from A to this 20 kilonewton force is going to be 3.5. So 20 will be multiplied by 3.5, right? So the distance from this A to this 4 kilonewton force here is 6. So this is 4 times 6. Alright. So if we do a calculation, you're going to have the sum of the moment A is going to be 3FB, which is going to be equal to 42. Right? Notice that we send the values that I send them across, so making it positive. So dividing this by 3, so 42 divided by 3 is 14. So FB is equal to 14 kilonewton. Alright, so this is 14 kilonewton. So now, since FB is equal to 14 kilonewton force, we have to use these equations to find the value of FE. FA plus FB is equal to 20 kilonewton. So substituting the value for FB, we have 14, 20 here. So FA here is equal to 6 kilonewton. So now that we have found the unknown forces, we can go about by just giving them a value. So let us try to analyze the beam for a moment. As you can see, we have 14 kilonewton force here. We also have 16 kilonewton force that we have just found, right? So the reason why this is larger than this one is because we have a distributed load that is acting on the support, right? Which is going to make this larger than this one. Here, we don't have any distributed load that is acting on the support. So in this case, there are more forces on this part of the beam than this side. So because of this, we have a lesser force on this side than this side. So the next thing we have to do now is to draw the graph of the normal force, the shear force, and the bending moment. All right. So the normal force, we want to take into considerations of the forces in the x direction. That is the normal force. But for the shear force, we are going to take into considerations of the forces in the y direction. Right? And the bending moment is just the integral of the shear force diagram. Let's try to redraw this beam in order to draw our graph. So now, since we have redrawn this beam, we are going to figure out the point that deformation is going to occur. So if you see this beam here, all these forces and the beginnings of the uniform distributed load, there will be a deformation here. There will also be a deformation here, right? So these forces are applied to this beam. So in that case, we are going to represent that with a vertical line, right? Here is the positive direction. If it is going in the positive direction, then below is a negative direction. If it is going in a negative direction, this is going to be the graph of our normal force. When the force is going out of the material, we are going to consider that as positive. If it is going into the material, we are also going to consider that as negative. We are going to consider these two forces as a force that is going out of the material. And this one is going to be going into the material. For instance, if you take this force and place it here, it will be pointing toward the distributed load, right? So in that case, we are going to consider this one as a force that is going into the material. So now for the normal forces, we have a horizontal force here which is going out of the material. So we have 2 kilonewton force that is going out of the material, which is positive 2. All right. Our graph is going in a positive direction like this. And from the 2 kilonewton force to the point of action of this force that is also going on the left, there is no force in between. And we also have 4 kilonewton force that is going out of the material, which is also positive. So the graph is going up again. But since we don't have space here, I'm just going to draw this graph shorter here. Add this to this is going to be 6, right? 6 units long. Just disregard the length of it because we don't have more room to create. So, and from this 4 kilonewton force to this force, there is no force at in between. So we have a straight line going to that. And this 6 kilonewton force is going into the material, so it is going to be negative. So in that case, the graph is going to take us down to negative, which is 0. This is going to be the graph of our normal force. So now the next graph is the shear force. For the shear force, we are only going to consider the forces in the y direction. The graph is going 4 units long. We call this 4 units long here. Negative 4 here. Alright. So, and from this 4 kilonewton force here to this force that is going up, there is no force that's acting in between. So we get a straight line. Right? And this 6 kilonewton force that is going up in a positive direction, if we subtract that from this negative 4, is going to take us to positive 2. Right? So, it's going to take us to positive 2. Got that 2. This 2. Right? So, from this 6 kilonewton force to the beginning of this distributed load, we don't have any force that is acting in between. Alright, so that is going to take us bigger straight, good, to that point. Notice that we have a distributed load. So in order to graph the sections of the distributed load, you will have to multiply this section, this 4 kilonewton, by the distance away from the side. So which is 4 times 2, that is going to give us 8. The result should be subtracted from the 2 here, which is going to take us to negative 6. But how would the graph of this section be drawn? Notice that if you have a straight line, the next graph for that is going to be an inclined line. And if you have an inclined line, the next graph is going to be a parabola line. The next graph for this one too is also going to be a cubic line. Alright? So in this case, the distributed load is a straight line. So the graph under that is going to be an inclined line. Negative 6. At the directions of this negative 6, there is a force that is going up, which is this force, alright? And that force is 14 kilonewton. So 14 minus 6 is going to take us 8 unit long distance. 8 here. The same method we use to draw the graph here is the same method we're going to use to draw the graph in this other section. And we are also going to consider the uniform distributed load here. So the distance away from this force to this force here is 3. So we are going to multiply this 4 by 3, right? It's going to give us 12. And since it is pointing down, is going to be negative 12. So negative 12, if you subtract that from this 8, it's going to give us negative 4. Negative 4, right? So, and it is a straight line, so it's going to be an inclined line. The last force we have now is this 4 kilonewton force, which is pointing up. So since we have negative 4 here, and we have 4 kilonewton force that is going up, that is going to take us to 0. Alright? It's going to take us to 0. So now this is the graph of our shear force. So the next graph now that we need to draw is the graph of our bending moment. Now this is going to be our T graph. Positive is going to be a negative also here. So the next graph now that we need to draw is this bending moment. Positive and negative here. So in order for us to draw the graph of this bending moment, I would like for you to take a few things into consideration. The first one has to do with the sign convention. Since we consider the anti-clockwise as the positive direction and the clockwise as the negative direction, so in this case our graph here, if it is positive, it is going to be negative on our bending moment. If it is negative, then it is going to be positive on our bending moment. So it's just going to be the reverse. Right? Since the height of this graph is 4, we are going to multiply it by the length, and the length is 1 meter. And because it is a straight line, it is going to be an inclined line. Alright. So positive 4 here. Good. The next one is a positive, so the graph is going to be a negative, right? And since it is 2, the height is 2, we are going to multiply that by the length, which is also 1. So 2 times 1 is 2. When you subtract 2 from 4, it's going to give us 2, right? So it takes us down to 2 unit. So the graph here, 2 unit. Cool. So now you got to be very careful with this section. Whenever you have a graph like this, always perform this trick. The distance here, right? Since the height is 2, just multiply that by the moment here, right? By this 4 kilonewton. So we multiply this 2 by this, it's going to be 8, right? So just subtract it from this value. It's going to take us down to negative 6. And now the next area is to draw the graph of this section. Notice you got to be very careful whenever you want to draw a graph of this section. Whenever you have a line passing through this this horizontal line like this, and it is an inclined line, I'm going to give you a very easy trick that you can perform always in this case. So the first thing you do is to divide this section into 2, because it has been divided. You can just divide like this. Good. Since we have divided this into 2 equal halves, and the distance from here to here is 2, that means each of this is going to be considered by us as 1. 1 here, the distance from here is 1, the distance from here is 1. It is going to work out. So in this case, we have the height as 2. So if you multiply 2 by the distance, it's going to give us 2, right? So 2, since it's a positive, it's going to be negative on our graph. So that is going to take us down to 0. It's going to take us down to 0. Notice that it is an incline, so it's going to be a parabola. Considering the height of this portion, we have 6. 6 times 1 is 6. All right. So since it is in a negative direction, it's going to be positive. So it is an incline, so it's going to be a parabola going all of this. But the distance from here to here is 3, so half of 3 is 1.5. And the height of this portion is 8. So 8 times 1.5, that is 12. So subtracting 12 from 6 is going to take us down to 6 again. So the graph of that is going to be, saying it is an incline, it's going to be a parabola line. And the height of this last section is 4. Multiplying that by 1.5, 4 times, it's going to give us 6. So that also takes us to 0 as well. So that is the graph of our bending moment.